drink of water real quick?
Yeah.
You say yeah.
All right, guys, ready? So we have a problem, okay? We have a problem here because up until now we've been measuring the distance. First of all, we measured the distance the car traveled. That was the first thing we did. But then we realized that distance traveled isn't a great way to express this because for this guy, the purple guy, for example, his distance traveled would still be a positive number, but he's moving to the left, and so that doesn't really make any sense. So what we decided was distance wasn't great, but then yesterday you said, well, let's do distance from the zero line, which I actually really liked, distance from the zero line. The problem with distance from the zero line is that if you look at this orange buggy, after this orange buggy, it starts here, all of a sudden it's going to be this way. It's still moving a distance from the zero line, except for the fact that, what do you notice on this axis? If you drew this axis down here, okay, what would be true about these numbers down here versus these numbers up here? That's right, these ones down here would be negative. And can you have negative distances? No, you can't have negative distances, true? So because you can't have negative distances, we need something better than distance. So we need a word that talks about basically where your object is relative to the zero line. Okay? What word are we going to go with? Yeah?
Position.
Position, that sounds great. I love that. Perfect. Let's go with position. I love you guys. You guys are so good. Okay, let's go with position. Let's go with the position. So this is what we're going to go with. So we're always going to, from here, talk about the position of the object or the position of the buggy. Is that cool? Now, we'll talk about that. There's a small problem with it, but it's not going to manifest. Let's do the red one. Okay. Can you see the red buggy's line?
Yeah.
All right. Is it straight?
Yeah.
Okay, let's write a mathematical equation for it. You guys already did this on your lab, but I'll do it with you. What is the general straight line equation? What's the general equation for a straight line? Y equals? Y equals, wow, look at this red. What's that? Oh, you want to do the decimals. All right, so here's what we're going to do. Look at the axis. What is on the vertical axis? What's on the y-axis?
B, or like your your intercept.
We're going to get there eventually. We're going to get there eventually. But in general,
Numbers.
what's on there?
Position.
It's the position, right?
Position.
Okay. So I'm going to write POS for position. Position is equal to, what is the M in MX plus B? It's the slope, right? Yesterday, you guys told me something very specific about the slope. We left it up on the board. What does the slope of the line tell you about your car? Not the speed.
Meters per second increase.
Oh yeah.
Okay? It tells you the position is increasing. What does it actually tell you? What does that number tell you? It tells you the velocity of the car. Right? It tells you the velocity of the car. What letter do you want to use for velocity?
V.
V. What's on our x-axis? Time. What letter do you want to use for time?
T.
T is good. Now, what is the B? What is the B? Okay, it's the intercept on the graph, right? It's the starting position, true? It's the position when. That's the question. Okay? It's the position when we started looking at it, right? When you started the stopwatch. So what time is that?
0.
Time 0. So here's how we write this. We write it position, and then we write a little sub-0 next to it. So it's a subscript 0, and it tells you it's the position at time 0. Now, oftentimes you'll see this just like this, and if you write it like this, it's perfect. But to try to confuse you, okay, they do something. They oftentimes use the variable x for position, because it's like the horizontal position. So you might see this way also. So the position is equal to the velocity times the time plus the position at time 0. These two statements are equivalent. This is just using POS to represent the position. This is using X to represent the position. Okay? What I like about this is this right here, this is the position at time 0. It's literally where it started. Is that cool? Is that okay for you guys? So far, so good?
Yes.
You want to see something interesting? You don't have to write this part down. This is just, I actually just find this interesting. Yeah?
Why is there 2 positions? Or,
Like this one, like this one, and this one?
yeah, like why are?
This is the position at time 0. It's the starting position of the car.
Okay.
This is the position at whatever time this is.
Oh.
So for example, if you put in 1 second, this would be then the position at 1 second.
Oh.
If you put in 0, what's 0 times velocity? 0. So the position would be the position at time 0.
Oh.
Is that cool? Just a real quick, this is not, like you don't have to write this down, just watch for a second. You guys told me here that the slope is the velocity, true? Is that what you told me? Do you know how to calculate the slope?
Rise over run.
So we're going to use a little rise over run. Is that okay? Now in your math class, what did you do? You do like the change in the y divided by the change in the x, true? Let's go over here and look at that and see how this manifests. I just find this interesting. I wanted to look at it. Is that cool? So far, so good? So when you look at this, this in your math class is the change in the x, but what is it for us? It's the change in the, you guys know this triangle?
No.
Oh, I'm sorry. I'm glad you mentioned it. This triangle, we use it in science. It means the change in something. Okay? This triangle, it's actually the Greek letter delta. It means the change in something. And it always means the final value minus the initial value.
Yeah, we don't.
You know, you may have, but what happens is you see it in a new context and you don't know it means the same thing. And if I just say it, you're like, I still don't know what you're talking about. Or what if you were absent that day? Okay, I know I'm boring you guys a ton today. Try not to fall asleep. I'm going to go quick and then we're going to do something else. I hate this. This is killing me. But you guys are holding on really tight and I appreciate it. All right, so here we go. So if we continue down here, so this is not our change in x, but our change in time. So what's on this axis then?
Change in position.
It's the change in position. So in your math class, it's the y, but here it's the position axis. See what I'm saying here? So this looks weird because it's this minus the, or over this. Now, watch what happens, because I find this interesting. If this is the change, it's the final value minus the initial value. True? But what is the initial value? The initial value is the starting point of your object. And so you end up with this statement right here, x minus x0. That's the change. And then what do I have down here? The time minus the time 0.
Wait, do we have to know this?
No. Why do I find this interesting? Okay. I find this interesting because what I'm going to do here is I'm going to look at this. So the velocity is equal to x minus x0, that's the top, divided by t minus t0. But what is t? What is the time at 0 time? It's 0, right? So I'm going to make it 0. What's cool about this is that if I multiply both sides by t here, I end up with vt is equal to x minus x0. So this is t minus 0, which is just t, and I multiply both sides. And what I end up with here is something interesting, because what I'm going to do is I'm going to add this x0 to both sides. And if I add this x0 to both sides, I end up with vt plus x0 is equal to x. And what that means is that if you want to find the position of your object, you take the initial position and you add on this vt. but that's what we have right here. You see we have the same statement here and here? I know, it's not that big of a deal. I wanted to point it out that whether we define the slope as the velocity and then we work through it, or we use the y equals mx plus b, you end up with the same result both times. Okay? Fantastic. All right. Whew. You are going to need a neighbor and a brain. Are you ready? New graph. New graph. What do you notice about this graph compared to this graph? There's some things that are different, there are some things that are the same. Tell me one thing that's either the same or different. Yes?
The x-axis is the same.
All right, horizontal axis, still time. Great observation. Give me something else.
It says velocity instead of position.
That's right. So what you guys are going to do is you're going to create a velocity time graph instead of a position time graph. So over here we have a blue buggy, a green buggy, a red buggy, a purple buggy, and an orange buggy. You can do them in colors. You can label them 1, 2, 3, 4, 5, whatever you want to do. You can do dotted lines and dashed lines or whatever. But over here, you're going to draw the velocity time graph just for the blue one. All right. So on your page, draw the velocity time like I've drawn it. Draw it for the blue one. Check your neighbor. Draw now. Quickly. Check your neighbor and draw now. Okay. You must check your neighbor. Okay. You must check your neighbor. So we think about the bus flow. The way you're going to get a constant speed. It is, right? So if the speed is constant, then the velocity is cool. So the question is, as the line goes up, is the velocity?
Didn't put it in my research. So how do you draw that?
Hi.
Hi, please.
What's what? You need some paper? Go still some out. There's a printer down there.
Don't steal a lot, Joe.
What do you think?
I think I know what it looks like.
What's the velocity graph going to look like? Draw the velocity graph for the blue one.
I don't know.
So just
Yes,
horizontal.
I should, well, no, because I heard something.
That's okay. But this would mean, as time goes on, the velocities increase. That's
I think
velocity is speed.
It just depends on what we're doing.
We're talking about these buggies. When you put the buggy down, does the buggy speed up? It speeds up.
I speed more rapidly.
What happens to the speed of the buggy? Does the buggy speed up or does it stay the same? The buggy stays the same, right?
Oh, so
This would indicate that the buggy was moving faster. That would indicate the buggy was the same speed the whole time. Draw.
Mr. Patton.
Yes. Well, I would put it right down the line. Okay. All right, guys, ready? Now, here's what I want you to remember. When we did the lab, we set the buggy down back here, and when we started looking at it, it was already moving. True? So the buggy's already moving. So when I go to draw the blue buggy, is it going at a constant speed? Which means it's going at a constant velocity. Is the blue one moving to the right or to the left?
To the right.
Right.
Moving to the right. Tell me about the slope of the blue line. Tell me two things about the slope of the blue line. The slope, not the value, the slope. Remember, slope is the steepness. Yes?
Is constantly increasing.
The slope is constant. The value is increasing, but the slope is constant. Right? If I run this along here, does it ever get steeper? So the slope is constant. That's one thing. And is it positive or negative slope? It's constant positive. So because the velocity is the slope, we draw here. Constant positive.
Oh.
I was right.
Nailed it. Ready? Do the green one. Do the green one. Do it now.
They're all the same buggy, right?
No, the green one, what do we know about the green one?
Steep.
Under,
Green one's slower.
yeah,
Yeah.
Mr. Patter, you need to teach him how to make straight lines.
It's in the thought that
You need a school line.
My lines at school. You do